Hello and welcome back to AP Pre-Calculus. Today's lesson 2.7 is on function composition. So just like in the real world, the idea of a composite means putting many things together. If you want to think about baseball bats or road bikes or canoes, all sorts of different things are made of composite materials nowadays. That just means they're using multiple materials to build something new. And that's what we're going to do, but we're going to do it with functions, okay? So we got this function f of x, and it is set equal to 2x minus 3. So we want to evaluate. Evaluate means we are going to substitute something in place of something else, okay? So in this case, you can see that I'm doing f of 5. I replace the x with a 5. So what I'm going to do on the other side is replace the x with the 5, and it looks like this. And now it's an easy, solvable problem, and we get 7. All right, so over here on B, I have an x here. Inside the parentheses, I now have 5x minus 1. So I'm going to substitute 5x minus 1 on the right side anywhere I see an x. So it looks like this. And we like to clean things up here in math, so we're going to distribute that 2 and get 10x minus 2 minus 3, and we get 10x minus 5. And that should be familiar to you. We did it last year in Algebra 2. So the idea of a composite function is sometimes in math we're going to put a value into one function and get an output. We have an input, we get an output, and we're going to use that new output to put in another function. So we're using the output of one function as the input of the next function. So let's look at example 1 here. So we got g of x is equal to 3x plus 1, and they said, hey, let's let g of 2 equal c. So we have to find out what c is. So I'm going to come over here to the g function. I'm going to replace the x with a 2, and I get 7, right? So now the c equals 7, and I want to put it back into the g function again. So I'm going 3 times 7 plus 1. See how I use the output of the first function, even though it's the same function, I use the output that I got there as the input into the next function, and I get 22. So we have two ways of writing notation for a composite function. All right, so here you see on this side, this is my favorite way to write it. I like this because it gives us the idea of simplifying stuff that we learned a long time ago. We work from the inside of the parentheses and work our way out. So this makes a lot more sense mathematically to me. You could write it like this. The reason I don't really like this is because of that guy right there. That's a new notation for a lot of people. That is not a multiplication sign. This and this are totally different ideas. The top one, we really are multiplying the two outputs we get when we put x's in. The bottom one is the composite. I'm going to use the output from the g function and put it into the f function, okay? But you might see it written in both ways. What I do is if I have a problem and it's written like this, before I do anything, I rewrite it like this one over here. I don't even mess with this type right here. So we read these two things the exact same way. We read these as f of g of x, okay? So either way that they're written, it's f of g of x. And if you look down here at this little notation right here, they're not the same as multiplying, where multiplying 5 times 4 is the same thing as 4 times 5. Composite functions don't generally share that commutative property. So when we're working with composite functions, we want to work, if it's written like this, you want to go right to left. That's weird to me, so I don't, like I said, I don't write it like this. I write it like this, and I work inside out. So g of x is on the inside, so I'd work with that first. I'd get an answer for that, and that answer is already in the little input area for f, so that's the way I like to do it, okay? So let's look at example 2. So we have two different functions here. I want to start with the g function first, so I know that that's the 2x. I'm not going to put an x. So that's the g function. I'm going to put a 3 right there. All right, the f is still down here, and I get a 7. Now I can go to the f function and put the 7 in there, and I get 21 minus 15, or minus 5 is 16, right? And you'll see here, I just switched the order, so that's like a commutative idea. I'm probably not going to get the same answer. So let's start with the f function. 3 times some quantity minus 5. That quantity needs to be a 3 because it drops down. Remember, this is the g function. So I have g of 4. So when I go to the g function, I get 9. See, they're not the same, so they're not commutative. Sometimes it might work out that they're commutative. Well, they're not really commutative. We just so happen to get the same answer, but that's a very rare occasion. So look at C. I don't like the way this is written. So before I do anything, I rewrite it like this. F of 2. And now I'm just doing my inside out kind of idea. 3 times 2 minus 5 is 1. So that's f of 1. 3 times 1 minus 5 is negative 2. Pretty simple. All right, so when we are doing composite functions, sometimes we're not just putting in numbers. Sometimes we might put in letters. We might put in a whole other function, right? And we got to be able to do that. So that's what we're going to do in example 3 here. So let me rewrite the equations that we had in the last one. All right, so there are my functions. And look what's inside on this first one, g of x. Well, I already know what g of x is, so I don't really have to substitute anything in there. I know it's 2x plus 1. But now my input for the f function is 2x plus 1. So I'm going to take the x out, and I'm going to put 2x plus 1 in its space. And then I'm just going to do the math, right? So we got 6x minus 2. Let's try b. I'm going to rewrite it because I don't like the way it's written. All right, I already know what the f of x function is, so I can take that f of x out because I know f of x is 3x minus 5. And then I'm going to go to the g function. I'm going to put 3x minus 5 where the x goes. Do a little algebra here and get 6x minus 9. All right, example 4. A little bit of a misprint here. We don't have a p function, but we have 3 other functions. And if I haven't said this before, that is why we don't just use y's anymore, because if they were all y equals, then if I told you to look at this function, I'd have to say the whole thing, where if I use function notation, h of x, g of x, f of x, all that, I can just say, hey, look at the m of x function, and you know where to look, okay? All right, so let's see what we got going on. So the first one I'm going to do is I want to go to the h function, right? So I'm going to put my k down. My h function is 2 times x, but I'm going to put a 4 there, minus 3. Well, 2 times 4 is 8, minus 3 is 5. And then if I go to the k function, I got 5 squared plus 4 times 5. Notice I'm just taking out the x's and putting in the input from the last function. And a little bit of math gives us 50. All right, let's look at b. Rewrite it. You don't have to if you know how to do it the other way. I just like to rewrite it like this. So you don't have to do this part where I'm writing the h on the outside. Like, it really doesn't matter. But I'm going to the m function, take out the x, replace it with a negative 2. And that's going to give me negative 6 plus 2 is negative 4. Then I'm going to go to the h function, take out the x, put in negative 4. Composite. I'm mixing functions together to make a new product, okay? What is that? Negative 8 minus 3 is negative 11. And last but not least, rewrite it. So this time, I'm not putting a number in. I'm putting in an x, which means my answer is going to have an x in it. So if ever I put in a letter instead of a number, that letter will be in my answer. Like if I said m of w, w would be in my answer. So I'm going to put the k here. What's the m function? 3x plus 2. Then I'm going to go to the k function. Oh, they were mean to us on this one. And I'm going to take out the x and put in 3x plus 2 on all of those. All right, we're going to have to FOIL this bad boy. If you learn the rule, it's a lot easier. The way I like to do it is I like to square my first term. move over a little bit, square my second term, go back to the middle term, and I'm going to multiply these two guys together. 3x times 2, this gives 6x, but because we're squaring it, we get 2 of them, so that's plus 12x, and then just keep distributing, and then combine some like terms. I got a 9x squared. Let's see, a 12x and a 12x is 24x, and then a 4 plus an 8 plus, that gives me 17. Okay? All right, so here on example 5, we're given a graph, and notice the graph isn't smooth. It doesn't have all just nice little curves and stuff. So I know that this is probably some sort of a piecewise function, because it's got some herky-jerky stuff going on. If it was a polynomial function, it would have nice smooth curves and all that kind of good stuff. Okay, so let's read it. The figure shows the graph of the function f on its domain from 0 to 9. So there's one function. And then it goes on to say, hey, we have a function g, and it's given by this 1.2x cubed minus 4.7x plus 9.62. So we want to know in a-1, the function h is defined by g of f of x. Find the value of h when we're putting 6 into the as the x value. So I have to work inside out. So I'm going to deal with this f of 6, right? So my f function is a graph. So I don't have anywhere to substitute the 6 into. So I'm going to go to 6 right here, and I'm going to see what my output was. Well, my output was 1, right? So I can go back, and then I need to do g of 1. Then I can come over here to 1.2 times 1 cubed minus 4.7 times 1 plus 9.62. And we're just going to throw that into our calculator if you need to, or if you can do it in your head, that's great. And I got 6.12. All right, now we have a lot of things going on here. I have the same f function. I have this new g function over here. I have an h function. Now that h function over there, that is called a piecewise function. So if you get an input of less than 1, you would use this problem here. If it was exactly 1, you're going to get -4, and if it's greater than 1, it's going to be negative x. Okay, so that's what that means. And then we got k is a quadratic function with a horizontal translation of 2 followed by a vertical translation of -3. So this is probably where I would start, because I probably should write something down for this guy. So let's do that real quick. So there's that function. Just remember, if my horizontal translation is a +2, then it had to be the opposite on the inside. So there I have 4 different functions, and they're going to ask me to do some composite functions work down here. So why don't you pause the video and see if you can come up with these 6 problems. All right, for the first one, I had to do g of 7. So I had to come here to the g function, the input of 7, I got an output of 4. So now I'm doing f of 4. So I go to the f function, I have an input of 4. What did I get out? I got a -1. All right. On b, the first thing I did is rewrite it because I like it this better. So I'm starting with my f function. My input was 7, so there's my input. I find the graph. The output was 2. So now I have g of 2. So I go back to the g function, go to my input, find 2. My output is 3. All right. For c, I rewrote it. I go to my k function. That's this guy that we rewrote. I put a 0 in for the x, worked it out, got a 1. Then I put the h of 1, so I have to go to the h function, and h is equal to 1. So I go here, and I got a -4 as my output. Let's keep going. All right, so it's written in the right order here. So I go to f function. My input was 8, so that's right there. I go find the graph. Well, the graph is right there, so it's a 0. So now I'm doing f of 0. So I go to my input of 0, find the graph. My output was -3. All right, so on E, I had start with h of 1. So I go to my h function. 1 is -4. So I put -4 in there. I'm doing g of -4. I go up to the g, find the input of -4. My output is pi, so I get pi. Last one. So I rewrote it. K of -1. I go to my k function, this guy up here. I substitute in -1 where the x is. I get 6, so I get g of 6. So I go with the g function, find 6. My output is -2. And that's how you do all these weird composite functions when you have many, many functions. All right, example 7. We have a table here. We got an f function, we got a g function, and the h function is the composite function of f of g of x, and they basically want us to substitute it in a 1. So I'm going to go here. My input is 1. So my input is 1 right there. Go down to the g function. So now I have f. The output of the g function when at 1 was 0. So now my input is 0. Go back to your input, 0. Go to the f function. It's -1, and that's right there. Not a lot of work on those. We like those. Last example. The function f is given by this quadratic, x squared minus 3x plus 7. The function g is given by this one, 3x plus 5. Which of the following is an expression for f of g of x? So I would definitely at least write this part out. Take out the g of x. We know what it is. It's 3x plus 5. And then go to the f function and do 3x. Put the 3x plus 5 everywhere you see an x, right? And that is not one of my answers, right? So automatically, I know that I'm going to have to clean this up a little bit. Now, I can get rid of 2 of my answers already, okay? My first term is squaring this guy. So 3x times 3x. So it can't be A, and it can't be D. So I know it's got to be B or C, but let's go ahead and do this. Remember my shortcut. I square the first term, move over, square the second term, multiply these 2 guys together, that's 15x, and then double it because it's FOIL outside and inside. So that's 30x. Distribute the -3. All right, let's clean this all up here. All right, so I definitely got a 9x squared, but I knew that. I have a 30x minus 9x. That's a 21x. I could probably stop there because I don't see 2 of them that have 21x. But let's just do 25 minus 15 is 10. 10 plus 7 is 17. And we have B. And that's it for today's lesson.